Okay guys, well my name's Graham Williams. I'm from a company called RMS based in the UK. Mechanical engineer for 40 years. I feel like a dinosaur to be honest, it's that long. But background is HNC, mechanical engineering, and obviously been involved with predictive technologies for the last 30 years with RMS. Today's presentation is obviously about a technology called motion amplification, which I'm not sure if you guys have got any background in this at all, but it's basically visualizing vibration. I know my friend over there from HD is involved with it himself, what I would say is as we go through the presentation, because there's a lot of video content in here, rather than wait till the end to ask questions, by all means buzz in at any time. And that way we can answer there and then based on any video fact, you know. Don't wait till the end, we can assess them as we go through. So what we're all about is cameras everywhere in today's world. Well, I'm over here from the UK and I'm getting notifications of who's going to the house now on doorbells and all the rest of it. You know what I mean? Technology is moving that fast that we know there's cameras everywhere. Obviously looking in new galaxies and all the rest. But for now and today, we're all about vibration and machinery monitoring. And just over the last 5 years, there's a company called RDI from America that have developed this camera to allow us to visualize vibration. And that's what we're about today. We use this extensively, this camera, and basically it's like another tool in our toolbox for vibration. I'm a diagnostic field service engineer, and we normally take vibration measurements, lubricant analysis to find the condition of machinery. But with this new tool and this camera now and the software that's being developed, it really is a game changer for us in giving information back to maintenance engineers and all the rest that make the final decisions on machinery schedule maintenance. And for you who have not seen it, I know the HD guys have got a camera set up there on a tripod, but basically it's as simple as a tripod with a video camera there, cable, back to imaging facility on software where we can manipulate the images to suit what we want to see. Okay, so basically this is how we visualize vibration, and it is as what you see on there. We use various different lenses. We can focus the camera to look at a machine. Now normally in this situation we would go around, if people are used to this type of technology, with vibration analysis with sensors in triaxial measurement planes on each of the bearing locations of the motor and the pump. We would then analyze that data relevant to a spectrum or a time waveform, complex data plots, to give to a maintenance engineer. Maybe this report can be about 30 pages long. Maintenance engineers today look at this, they don't really understand it, nor should they. They look at it, all I want to know is what's happening with my machine. So this is a standard footage of the camera of this machine actually running, motor and a pump. I think I can do it off here. No, sorry, I'll have to do it off. Okay, now when we motion amplify it, you'll see the difference when the line comes through. This is what is actually happening. Okay, so this allows us to look at this machine and visualize the vibration rather than look at spectrum and data plots. Standard footage from video and motion amplified. You can see the vectors on there showing which way and how that machine is moving on its base. From this bed plate we can also take data plots from vibration spectrum, waveform, and all the rest of it. So there's a lot going on there. I'll come back to that in a minute because these videos go quite quick, we should slow them down. But we can take standard footage and then we can take motion amplified signatures and allow us to visualize what's exactly happening. Now in this instance there now we're going to show you a situation where this is a British sugar plant in the basement of a cellar where you've got a motor that's offline, pump set, and a pump set that's offline. The only one that's running is this new pump over there that they put a new motor on, but the primary part of this maintenance repair was to put a new section of pipework in there. That's all they were interested in. Not once did it cross their mind to look at the base plate and look at the poor situation it's running in. Fundamental repair was this piece of pipework up there. Now, let me just play you the scenario off here. So we've got two pumps offline and one online. Okay, this is what's happening with that pump running. Yeah. This is using a colour, and this allows us to zoom in into any little component, and you can see what's happening on each situation. Remembering, this isn't very good. You can't see this with the naked eye. This is how motion amplification works with vibration. There's the pipework that they were interested in. That's the motion that's occurring by these pumps on this. I'll go back to that side so you can see it again. We'll have to do it like this, sorry. Because it's part of the same slide. There's the first one that I showed you. Remember, these pumps are actually running. When you see the standard motion, the software allows us to look at the standard footage and then put the motion amplification on to see things moving and how they move. Now for us, this is a game changer from a diagnostic perspective, because we would just be getting that signature at the top that you can see there, the spectrum, and make a diagnostic decision on that. But now we're allowed to see through the feet and all the rest of it, really. Just play that again so you can see it. This is the colour camera, so you can have black and white camera, or you can pay extra for the coloured situation scenario. And we also have a high frequency camera as well, which I'll explain to you. So this is the situation of a British sugar plant, like I said. This is the base cause, and all they were interested in was putting that piece of pipe in. To them, that was the repair, that was the modification, and then they were worrying why they were getting pipe fractures at the welds.
Is that quite flexible engine?
It is, but yeah. Okay.
So they had multiple fractures occurring
In the pipework prior to the modification,
yeah.
but all they did was change the pipework, modified the pipework without touching any of the base at all. Didn't occur to them that anything like that was going on. Now, this is where it's so powerful as a tool. We can take vibration measurements of pipework across welds and reflect that against the Energy Institute guidelines for an ISO tolerance, and give that to a manager saying that pipework is out of spec across those welds. But if you show them a picture, and the video is so much valuable than information written down like that. And you know, it is a game changer from a diagnostic perspective, because from a non-contact perspective, we don't have to put an accelerometer on any part of this component. We can step back from afar and we can put we call these ROIs, regions of interest, that allows us to take a measurement. This is in displacement. Okay, but in any effect, we can change that to velocity if we like to look at a velocity signature as well. We can add an ROI and any part of the image from the camera to take an actual measurement. Not just an amplitude measurement, but a frequency measurement as well. This is a setup. I know it's a bit. It is actually Red Bull Racing, who prior to them purchasing several cameras, they asked us would we do an actual study on a car in a wind tunnel. They wanted to check around the side pod, and I'll show you the video in a minute. So we can actually again put this ROI on, measurement section anywhere, and get any plot that we want to confirm vibration. How difficult would that be by putting an accelerometer on a non-magnetic piece of plastic to take a measurement? It would be difficult to do, especially in a wind tunnel. But this was something that we showed them we could do. Oh, sorry.
That would also be a case of affecting the outcome by measuring.
Oh, of course it would, yeah. And that's another point. It's a good point, that is, because obviously by putting the weight of an accelerometer on a plastic component like that, we're going to change the resonant condition and the natural frequency of that component.
So basically the camera, you don't have to install any device, and you're not on to give it any clues on what's going on. It only watches the image.
It's what's in the view.
Yeah.
Now I could put that measurement point anywhere in that image that we've got.
So that's a dynamic measurement point?
Yeah. So we can get that vibration signature, amplitude and frequency anywhere on that image.
Okay. So there's no need for a reflective device or anything on there?
No, they'll come to that later.
Okay.
I'll come to that. No. Please fire your questions over, because I'd rather do it at this stage, because at the end, you can do it from the various videos, and then we're more consistent. But yeah, There is an application called TaxSync that we'll come to later. The guys from HD know about it.
Okay.
And where we can freeze rotational movement as well. But in this instance, this was just for Red Bull prior to them purchasing the camera. Set up card in a wind tunnel, this was for them. I didn't actually do this, Andrew did this. You've met Andrew before, haven't you? So it's basically, that's the situation with the camera. So it's modelling the wind tunnel, it's modelling the mobility of the car, and we can get an amplitude from it. That's why it's, yeah, by all means take photos or...
Yeah.
Do you want me to play the video?
Yeah, please.
Okay, here we go.
My boys are Formula nutters.
Hey, no worries. Do you need to go in, all good? No?
Do it again.
Do it again? You let me know. I'm going to count it down from 3,
Okay.
because it's quite quick. 1, 2, 3.
Absolutely. Fantastic.
Okay, and after this, I think they sold about 2 or 3 cameras to Red Bull.
Yeah.
Okay.
I think it's a bit worse than Mercedes.
Mercedes didn't buy one. That's why they are where we are. Yeah. Okay, but that's what I'm trying to explain there. We're saying that's non-contact measurements, just basically from a camera, from a video shot. We're used to using accelerometers, going around pieces of equipment, like we've done for years and years, and still do, because we still have to combine both technologies to get to the diagnostic capabilities that we want. But this is a great tool for doing things that are non-contact. This is another situation where we're going to explain transient vibration measurement now, how to slow something down with the camera. If we're looking at something that's of speed and we want to slow it down to take measurements and see what's going on, this is the same scenario that you can use the camera for different aspects of what we want to look at. So this is a staple machine that we're looking at. So that's real time. And this is how we've slowed it down with the camera. Still, with a measurement point on the top there, we can slow it down and measure any part of the view. But it allows us, on high-speed processes, to slow that process down and zoom into certain areas, take measurements, and look what's going on.
What was the problem here?
They were damaged, sorry, I'll go back. This is me playing around offshore, seeing if I could measure the vibration on the chopper as it landed. It just proves that we can still take spectrum for frequencies, time waveforms and orbit plots relevant to an ROI on a chopper that's moving. This is a bit gimmicky, by the way, just for presentation purposes, but I was playing around and got a bit bored, really. So I just thought if we could do that, it's pretty good. So the slow motion, the staple machine, it was damaging the components as it come in, as it was clipping down. So they wanted to slow the process down. It happens that quick to see if there's any worn linkages or anything like that. So I didn't actually do that one, but it just shows you how, if you've got a high-speed application, you can slow it down and look in more detail. I don't know if you've come across bump testing. I know the guys from HD would have. So often is the case where we get a resonance situation, a natural frequency of a system that we need, that resonates when it's amplified by a forcing function. So often is the case we have to do a bump test, and what that usually means is we'll add an accelerometer to a motor or a pump, remember an accelerometer with a magnet base, and then we'll use an impacting hammer to impact the structure and look at the resultant response, which allows us to work out the frequencies, or the resonant frequencies of the system. In this situation, we've got a motor, vertical motor and a pump. We can actually do it with a camera now, which is much better because it takes away the additional forces that you spoke about of the accelerometer changing the natural frequencies of a system. So I'll just play it, just show you what I mean by doing that. So we're still impacting a structure and looking at the response of it. So there's the impact of the structure. There's our ROI, this is the frequency response of it. There's the time waveform, and this is the response at the bottom, which is a lot more stiffer. So we're just proving that at the top on a vertical structure which is more prone to movement, this will be more of a resonant situation than at the bottom where it's much stiffer with more mass. Yeah? Normally we do an impact test with a modal hammer and accelerometers maybe, but this situation we can apply the same procedure and get similar results. So the camera is quite good for doing things like that as well.
In a situation like this, you really don't have to worry about mass loading with an accelerometer.
Exactly, because there's non-contact.
No, but if you're using an accelerometer,
Oh yeah?
it's so light compared to the rest of the structure, you don't have to worry about the
No,
mass
no,
loading of it.
no.
But in the case of the Formula One car, that would have been a problem.
Absolutely, yeah. No, that's a fair point, yeah.
Yeah.
Yeah. If you've got something that's highly resonant, very thin,
Yeah.
then
sheet
like a sheet metal,
Yeah.
absolutely. But what I'm just trying to explain is that all the different applications of the camera, you know, we can measure non-contact, we can measure moving components, we can slow equipment down and processes. This is why it's such a great tool for us now. Now, I think we mentioned tackle before.
Sorry, one question.
Yeah, of course.
With the other situation,
Yeah.
can you do the bump test while it's running?
Yeah. No.
Oh, okay.
Hang
So
on.
you can't take a frequency response of the running machine, do a bump test.
The only way you can do that is through a vibration instrument, because we use a process called negative averaging.
Yeah.
And to answer your question,
Yeah.
why I'm laughing,
Not
so
with the camera.
not with the camera, because if that's stationary, static, because you just want the response of the impact of the hammer. If that's rotating, it's got a forcing function of imbalance or something like that in there anyway, and then you'll have another frequency to deal with. So the idea of a bump test to work out natural frequency is to take away that frequency and just leave the force of the impact and your resultant. Now, I don't know if you guys have ever been involved with this, but prior to the camera, and even now, if there's something running, say I've had to do this, oh, it was so embarrassing, in a mult on a conveyor with an overhang, and the only way we can do it is called negative averaging, where we put an accelerometer on there, and you've got your instrument, you set it up for negative averaging, which is going to take away the running, like exactly what you said, it'll do it, but the software and the analyze will do it. But if you've ever been there when there's a component running and people are walking past and you're hitting something with a hammer, it's not a good look. So, and then you have to explain to them what you're trying to do. But that's the only way I know of that to do that. It has to be static. But with another bump test, with an instrument, like you, Dash, I don't know if it'll do it, but it may do it. There's an option in the software called negative averaging, which, when I'm impacting it, it'll take away the background noise. So rotating components through MA now. I think you mentioned earlier. Obviously, with something rotating, we're just looking at the effects of the rotational excitation force. But what we can do, by putting some reflective tape on, and in conjunction with a tackle, we can call it, and there's a function in the camera that's called tack sync, which allows us to take away the rotation background and look at what's moving by syncing it to the tackle. Okay? And from this situation, again, you can see we can have an ROI, we can have a displacement waveform, we can have an XY displacement in microns, orbit, or various ROIs in any of the picture for measurements. But what you tend to get now, this is when you tack sync. So that's spinning, but what we're looking for is other things in the signature other than the rotational frequency that's happening with the tackle. It's very effective if you're looking at couplings and things like that, because that slows the coupling right down, but you can see the actual thrusting across there because we've synced it. Just another application, really. The guys from HD will be aware of this. We were looking at it earlier where you're showing. So this is a phase map. So with the camera as well, we can actually look at the phase measurements of how are things moving. So we can If you're aware of what phase is, I'm sure you are. It just means which way the actual vibration is moving relative to 360 degrees, really. But you can see in the corner, you can see, put a phase map on. It's quite gimmicky, but some customers like it. It's easy to explain, really, rather than put motion vectors on and things. But yeah, let's just look at the overview with it then. So measurement, movement, not visible to the human eye. Like we spoke earlier, standard video technology, high-speed machine-grade cameras, algorithms to extract meaningful data. But the thing is, different from vibration, each pixel in that camera field of view is an accelerometer. It's a measurement, it's a sensor. So the resolution and the coverage is exceptional compared to one instance with an accelerometer. We can go down to submicron measurement if we really amplify the video. So a frequency, a very small amount, we can amplify. And we can get measurements over 2,500 hertz with reduced resolution. So there are limitations with the camera, as these boys will tell you as well. So with a standard camera, the frequency range is up to 60 hertz only. After that, you have to start cropping, what we say cropping the video, but we lose resolution on that. So there's two types of camera. There's a low frequency camera and there's a high frequency camera, which allows you to look at various frequency ranges. More often than not, 60 hertz is adequate for what we're trying to achieve. But for instance, if we were looking at a gear mesh issue, which is a high frequency, which was the source of vibration, we'd need to look at the high frequency camera. We don't use it very often, but now and again we have to. So there are limitations in frequency ranges for the camera. Just so I'd let you know that. Industries and applications. Well, we cover a whole host of industries there, and this camera is flexible in all its use, really. It can be used in most rotational equipment, static equipment. I'm sure you're used to all these types of industries.
Yeah, especially the roller coaster.
Yeah. Yeah.
Where did they start using it? What was the initial drive? Probably defense industry or missile technology.
I don't know where they would probably. It's American, so you'd like to think so, wouldn't you?
Yeah.
It'll be something to do with,
Raytheon or
yeah, MOD or something like that. They all seem to come from there, don't they? But it's a very good technology, and it's been fantastic for us because it allows us to, I'm going to explain to you now about vibration analysis. Majority of the time, pre-camera days, we used to have to go around measuring, like you still do now, take routine measurements with accelerometers, take the signal into an instrument, allow us to measure spectrum and waveform. And these are complicated plots to people that don't understand what's in them.
that doesn't sell anything to management.
No, it doesn't. No, you're exactly right. And you try and explain somebody, if I can sit there in front of a maintenance manager without being rude, who's got no background in vibration, talking about synchronous and non-synchronous and sideband energy, he'd be asleep before I tell him what's wrong with it. You know? So to show him a video, oh, is that happening in my plant? That's different. So, but yeah, vibration analysis, conventional analysis allows us for spectrum, waveform. We can do multiple points on parameter trends, and it's a low cost per point. We used pre-camera days, we used to use what we call ODS software, which was very bulky and complicated, allowing us to put vibration measurements with a phase marker on, a tacho, and put as many accelerometers, maybe 8 channels as you could, and then try and feed all that information into a software package that produced, you know, a stick graph like that.
Is this from Emiscope?
Yeah, we used to use it, and it used to take forever and a day to model something, like just as simple as a pump structure. Oh, and you used to do it, so to visualize a larger structure was complicated and a high cost per point. The software was expensive, but the most problematic was it's time consuming. It used to do what we want to try and do today, it'd take hours, days. But now we've got this instrumentation which makes this process much easier. So measurement points are amplified, vibration becomes visual in playback. It's more, every pixel in the frame is a sensor. So whereby we're using one accelerometer, We got up to 2.3 million in some pictures that we take non-contact, and I say it's low cost per point. It is initially because the cameras. I'm not here to sales. I'm a service engineer, so they range from around 30 to 40,000 pounds, you know, to purchase. So where they say it's a low cost per point, it isn't initially. But like I was talking to the HD guys out there, back in the UK, we can charge up to, I don't know, over £1,000 per day for this technology to give them what they want. So the low cost per point is the payback is very, very quick for the camera if you can find the marketing for it. It's all about marketing the camera. We tick it out with every job we do. And if we were doing a vibration job, we might do a visual ticket. Because the camera sets up, as these lads will tell you, it's a 7-second video. Once the camera's set up, press a button, in 7 seconds you've got all that information. So, and to show somebody that, they might think, we'll give you that for free this time. But if you want any more, we'll do more detailed stuff on your plant. It's just like a little catcher really for any management out there. But, you know, it is low cost once you purchase the equipment. And the software's being developed regularly, like so. There's new components coming in all the time. And like I said there, 7 seconds it takes to take a video and it's done. Sorry, I need to explain that slide to you. So, technology overview. With the camera, we're always working in what we call the displacement field. Displacement is the ability for the vibration to move. It's actually moving peak to peak, and we're looking at the displacement of an object. So it's the movement of an object. The other units, velocity and acceleration. With the acceleration unit, it's the high frequencies, which we're not really interested in. We'd have to use the other camera for that. The velocity is in millimeters per second, like you lads will know, which is the ISO standard for us. So that's the industry standard. But the camera is working in this displacement field where we're looking at mainly low frequencies below 60 Hertz. So normally what we'd do with accelerometers, like I said earlier with ODS, we'd put accelerometers in these certain positions looking at a motor and a pump and get probably 8 channels back with a phase marker with some phase back to give us the operation deflection. That would be the setup we'd get normally with an 8-channel instrument. But what the camera does is each pixel is a sensor, a measurement point, so you can see how much more information we're getting back off a system like that. So it's up to 2.3 million pixels on some certain applications, which is great resolution and great feedback, hence the images. And like we said earlier, if I was to go to a maintenance manager with a signature like that and explain to him we've got a looseness and a bearing because that's a looseness synchronous signature, he'd look at me, okay, daft. But then if I played him this, which is the same signature, it's much more easier to get your information over rather than show data plots, you know. So this is
Sorry,
go on.
Magnification in the video compared to real movement.
Yeah, but the thing is with the camera, you can change the magnification up to 100%. So we can make it look worse than what it is, but you don't. All we're using that magnification for is looking for finite movement. So some instances where, you know, that base plate there could be just moving and twisting a little bit, we'd probably have to magnify it so we can make it visible. So people say, well, you can make it look worse than what it is, but ultimately we'd put an ROI on there and we'd have a vibration signature anyway. So you are in control of the magnification of the video up to 100%, you know. So, but the bottom line is, it's a diagnostic tool, really. It's allowing us to make a measurement and see exactly what's going on rather than rely on vibration. Yeah?
When I'm working on videos like this, I usually try to keep the same frame rate and similar magnification just for reference purposes. So when you watch the video, it's not different levels of application all over the place.
You're correct, yeah. Go on, no, it's good.
So the customer is seeing a relatively similar experience, but they should be in relation to each other and their amplitudes.
Yeah. So when we do compile a video, we can ask the video to say exactly what the amplification factor is, whether that be 25%, 50%. So, for instance, a before and after scenario, would it be on 25%? We'll keep it at 25% after they've done the mods, really. It's only there to allow you to look into finite detail, really, and that's how we should be using it.
I was just thinking about the sugar factory.
Well, you don't... Yeah, but all they were interested was that piece of pipe. They weren't interested in the base.
And this content.
Yeah, so basically when you start working with this, you start noticing artifacts. When you go into high amplifications, you start seeing shimmering artifacts. So it was a 75 amplification maybe or something like that.
I can't remember. It's not on there, but I probably think the lads would have put it up to 100% at that. See, I think where to go with it is from a diagnostic perspective, we would always have it at 100%, so we can see exactly what's moving in there. And then ultimately, we would take a signature, vibration signature. This is how we do it. We'll take a vibration signature of that with our instrument, and it'll read 10 millimeters per second. So then we will then put an ROI on the screen, do our velocity spectrum, and it should read similar. So it's always going to read similar with the spectrum that we think, what we select, but the amplification, we can make it look worse than what it is. But I think it's fair to say that it depends how much of an impact you want with you. If you want something repaired quickly, I think it's best to put it at 100%. And sometimes, unfortunately, with certain customers we use, think, put it up to 100%. Let's get this job fixed, and then you'll say, God, is it that bad now? We'll get it fixed. That's the type of thing we use. But yeah, it is flexible. But I think there's as long as you're using it in the correct manner, that's the way to do it, really. So like I said, it's a game changer for us. It's quick and simple to use technology. It's very easy to take on the training. The training of it, as I'm sure these boys will tell you, is quite simple. If you've got a little bit of a vibration background, it's easy technology to accept. It's certainly easy to use out in the field, and the feedback in the reporting and the videos is immense. So, like you can see. So you can ask yourself how much, and we tried to make sure that the amplitude coming back off these videos is very similar to what you do in a vibration test. Yeah, it's important. So, and it's relative to the distance you're away from the actual component when you're measuring it. We have a laser, like these lads will say, and we take a distance measurement off the laser to where the camera lens was to the component, because that's critical. That distance is critical in giving accurate amplitudes back. And we did tests with, like you said, like a thin plate, where we impacted and resonated off the 4 sensors, and we put 4 ROIs on there. And this was the return off the camera compared to the impacting and the ringing out of the accelerometers. For those who've got a vibration background, when you're using an accelerometer and you're trying to measure displacement or movement of something, you have to integrate that signal, not once, but twice, from acceleration to velocity to then displacement. Each time you integrate that signal, you incur errors. So it's bad practice to ever measure something with an accelerometer and show something in displacement, because you've integrated it twice, which incurs so much errors. We just don't do it. We can integrate once into velocity like we normally do, but never go again into displacement or on an overall level. We just don't do it. You stay in the unit that you're measuring. So this displacement, so the camera is more accurate for displacement than an actual vibration measurement. But one of the good things with this camera, which has come in over the last couple of years within the software, is frequency filtering, which is really important for us. I'm sure you lads would say the same. We can filter to an actual frequency of vibration. Now, if we look in this video, this is a video of a conveyor drive with no filtering on. So this is what's going on there.
Amplified.
This is amplified, yeah. Yeah, we'd like to think it was, yeah. But you can see what's going on. You've got a pump unit there, you've got a conveyor there, and you've got the head drive up there. Okay? And it's all going on, isn't it? Now what we do within this field of view there, if you were looking at certain aspects, which becomes fantastic for us, we can filter. So we can put a filter on this. We've put a 2 hertz bandpass filter on this, which is the output of this conveyor. Yeah? So we've taken away this, we're not interested in this. We can filter any part of the video to whatever frequency we want. So we can concentrate on what component we want. Next one was 25 hertz, which was that little hydraulic unit at the side. So we filtered directly to that. Yeah? So it just means in your certain videos we can filter to whatever component we want if it's got a fundamental frequency. And again, 4 hertz was the output of the conveyor belt over there. Sorry, I never played that for you, did I? So you can see just the belt's moving, conveyor screen at the back end. But rotating equipment, I'll just go through some case studies with you now. So again, skid plate before repair, motion amplified footage, 1 times RPM, we're looking at 20 millimeters per second, seal and bearing defects within 3 months. So you can see this scenario, can't you, of what's going on. And again, you can't see this with a visible eye, so it's ideal for bed plates and things, what you're looking at there, and how things are moving on the actual bolts. A lot of the time, bed plates are really poor, fixtures are bad, and this is, people tend to forget this. So there's the before and after they've done the repairs. And we can then show that as a video rather than trends and vibration data. Okay. This was a resonance issue which my colleague Dean was involved with. So again, a motor and a pump scenario, standard footage, and then he'll show you motion amplified, and you can see the back end of the pump there. There's a vibration measurement off the ROI off the pump in velocity with a little bit of an orbit plot there. So you can see how that structure's moving. It was resonant around this area. They did the impact tests. There's your bump test information. So you can put motion vectors on there to show you how it went. So obviously the stiffening went in after the mount, so that stiffened it, moved the resonant frequency outside the running speed of the motor and pump, and that's the difference before and after. Another one, which was pretty good, this is in a pumping station. So 3 vertical pumps that we looked at, and obviously the bottom pump was moving around on the floor. This is filtered to 880 RPM. This had a resonance issue. It's a variable speed pump. So you can see how the floor is moving. And again, this is invisible to the naked eye. So this has been amplified.
You'd feel this though?
Yeah, you'd feel it under your feet. But remember, this is filtered. So this is filtered to 880 RPM, which is the resonant frequency. So obviously there's not as much movement at the higher frequencies, the higher speeds, so it's more resonant around 800 RPM. Bump test filtered. There you go. Excuse the size of the sledgehammer. So you can see the filtered response. So that's a good tool to do once we do bump tests. You can see how we use the camera to highlight the frequency of concern, really. Again, this is a problem solving of a pump. Sorry. Standard video and then HD. So this had been rebuilt, this pump, and they had machining errors within this bearing housing. Only when they stripped it down did they see the ovality in the bearing housing that's causing issues. But again, to explain that to somebody, they wouldn't go down explaining that with vibration and spectra would be difficult for them to move into that realm, you know, of looking at their own issues with machining and all the rest of it. That's why, like I said to the guys from HD, it's nice to do a video on vibration data before and after a repair and things to show to the customer, you know, exactly what they're getting. It's really important that we do that a lot back at home, especially on turbines where, you know, if you're going to do a major repair, take the data before, do the repair and take the data after. Then it just negates any issues with warranty and all the rest of it. Covers your...
Can you play that again? It's a thick casting and it's flexing quite a bit.
Yeah. So what they found within that bearing, they machined the bearing housing, it was oval. So the bearing, I don't mean like an egg, but it wasn't concentric to the bearing journal. So the issues with the bearing, the pump manufacturer machined that, sent it back like that, and then they got the information. This is why we do before and after, that we can look at it. It wasn't like that when it went away. So it's been repaired internally, had a new impeller, new bearings, and look at it now. It's nice information to have, really. Piping. We use it a lot for piping scenarios. I think I spoke to the lads earlier about Energy Institute guidelines. That's our vibration tolerance, really, for measurement, small bore pipe work. It's recognised all over the world as well. So rather than look at certain scenarios of pipe work, when you're looking, you can do a big field of view like that, and you can measure certain pipe works and get a nice view of the pipe work, and then zoom into the area that you want to after. It's really good for looking at pipe work and piping vibrations. So this is amplified footage just of a structure, and then you can home into certain little areas that are vibrating as opposed to others, you know. From a good field of view, you can take a measurement there, you can get a spectrum, you can get the XY plot, all from afar. Whereby before you'd be hunting around with an accelerometer for days. You know, it's really valuable for that type of situation. You can see the difference between the standard footage and the amplified. So it's nice to show. But what we tend to do with it is look at this information and then put our tolerance on, like I say, the Energy Institute, and reflect vibration signatures from that. And that's the type of thing we're looking at, where you get, okay, concern and problem. So we know with a vibration up there at that frequency, we're in the concern. So it's nice to show the customer things like that. What have we got? Steam turbine one. This is Stu's job. He loves this. So basically, steam turbine, brand new going in, and they're concerned about all the pipe work that was running it. He set the camera up to 100 frames per second, filtered to 25 hertz, which was the frequency of the generator, obviously. So the output of the turbine, you've got a steam turbine gearbox here running a generator. Especially when you're looking at new equipment. People seem to expect everywhere, because it's new, it's going to be right. And often the case, it isn't. Sorry, I need to forget that one now. So before mods, this is the way the pipework was running on a brand new installation. And this is a major concern for us. It's small bore pipe work, welds. I was talking to the guy up there about, you know, pipe work and welds and things. It's a major concern. We have loads of opportunities where we have to go and diagnose faults in pipe work. And we keep reflecting this Energy Institute guidelines, and you can see the frequency of vibration. But what's nice to do is use it in live mode to determine certain situations, and you can see the effect. This is with the instrument though. We've measured this frequency at 22.5 Hertz, which is too close to the excitation force. So what you can see there, what we're doing there is using the camera live, and we're going to put a temporary brace in here and adjust it so you can see the vibration. And once you put the brace in, you can see the vibration come down to nothing then as he's tightened the brace up. So by using that live, you can get a great response as to what's going on. You can see the brace, the temporary brace there. So then you can make your actual design pipe bracing much more effective then. So that's before and after. Okay. Let's move on to that.
These guidelines from the Energy Institute, is it international standard?
Yeah.
For
Yeah, it's international standard, yeah. Yeah. Yeah, there's a proper specification for it all. You know, for small bore pipe work, large bore pipe work. Yeah. It's the only thing we got from a vibration perspective, really, you know, to reflect industry standards. So that's why we use it. You know, there's various standards out there for vibration as well. We use 101863 for normal equipment and 79193 for turbines, for displacements and measurements like that. But they've been there years and years and they've never been upgraded. And
10186 upgraded to 20186 just recently.
it may well have been,
I believe so.
but I don't think we're using that at the moment. But I think it may well be, though. It needed to be honest. So thermal growth. This is a situation where we were looking with the camera and we used the time-lapse situation with it where we could monitor something over a 2-hour period. So this is a vessel, turbine vessel, that was starting up, and obviously I can't remember if it was on the condensate side or what, but you can see by using the time-lapse function in the camera, you can measure up to 2 hours, and we can see how much movement went with thermal growth of this vessel. So the customer wanted to, having pipe fractures, we wanted to know if it was due to thermal growth over a period of time. So this is over a 2-hour period, and you can see what's happening there, and you can set your data plots off there as well to show you how much movement actually occurred in that vessel over time. So that's another function of the camera. You can see your measurements there, your displacement, X and Y, of whatever you draw the ROI to be. Tack sync. Right, I touched on this a bit earlier, and this is quite interesting. So this is the difference. We're referencing something that's rotating and using a tack or a reflective tip to sync to the speed of the rotating component and freeze it so we can see the actual, and this is a fan blade cracking issue we had in cooling fans. And again, this was Stuart's job, and we used tack sync to find out what exactly was going on. So there's your fan, motion amplification. Once we tack sync, we can see how the fan blades are bending. So this is the cooling section of the fan, and you can see the cracked blades. I can't even stop it. Yeah. So you can see how the cracking effect that was happening in these fan blades. severe cracks in them.
Is that the root?
Pardon?
The root of the blade?
Yeah, where it's mounted onto the brackets.
Okay.
So to find it out though, the MA setup, there's the photo tack, yeah, and your acquisition unit. There's your normal camera, but you've got to have a photo tack with this to work out what's happening. To stop the rotation and freeze it to the rotational speed, then you can look at the pure vibration. And you can see what's happening there in that fan blade. You can see the vibration up and down. That was what's cracking them on the bracket. That's the power of tack sync really. You can see the up and down movement. You can actually take the measurement as well. See,
So actually some rotation of that.
yeah. So during the rotation, those blades are moving up and down. And they were having consistent failures there and they're cracking. But you can't do that without syncing it to the tackle. So you can have it. So this is with the new fan design after they changed the design of the fan blades. And you can see the new fan and the old fan. It's still moving a little bit, but not as much as it was on the bottom.
That looks chaotic.
The orbit. Yeah. I'm just explaining what effect you can get by tack syncing, say, the old design and the new design. Transient events. Again, this was another British sugar factory, and this was with the camera set up. We've got a CM server here that's taking a lot of data. So he's moving a bit quick, isn't it? But we can have a trigger. So we're triggering off amplitude. So we're going to set this, because this situation, I'll try and stop it because it. So basically this inlet to this fan now, different flow states, but only at certain times was somebody noticing this vibration in the bottom thing there, in the bottom support. So because it wasn't happening all the time, we had to set up a camera over a CM server to look at all this data and use it as a trigger. So we set it up where only above a certain trigger did the camera come into it and start recording, because normally it was okay. And it was, over the long-term trend, it proved that when the flow rate become lower, did it cause this brace to actually move about.
Was it a function of the flow rate?
The flow rate and the resonant frequency of the weak support, and there was a crack in this base. Obviously we've highlighted it here, but at the time you couldn't see it with the motion vectors. So by putting the vectors on, you can see the different amplitudes and how it's moving. But it was only at a certain flow rate that this occurred.
Graham.
Yeah.
I was wondering, how long time do we?
Have to go.
No, how long time do we need to just finish it?
Finish 5 minutes.
Yeah. 10 minutes, 15 minutes is plenty enough.
Oh gosh, yeah.
Yeah.
Sit.
Then I'm leaving. But
Yeah.
I will tell them that next is coming in quarter.
Is somebody coming in after this?
Yeah.
Okay.
In 15 minutes.
15 minutes. No, I'll fly through the rest now.
Yeah.
Because I think the guys have got what we're trying to do, you know, just trying to show off. Yeah?
But if you need 30 minutes, we can.
No, I don't need 30 minutes. I've only got 5 slides to go through. Just an oil skid pipe failure. This was actually a situation where the pipe let go. So we're monitoring this because they've got issues with piping issues here. And you'll see this for yourself. So this is genuine as well. So this is amplified and they've got an issue here. So they've had issues for a while, but they can see a little bit of movement visually here. And this is, again, Stuart's job. He's not very lucky, Stu. So you can see this pipe work is going to go.
Oh wow, it's gone.
Yeah, it's gone, yeah. But it goes again at the back. So this was just a study because they thought they had vibration there. So
Capturing this within 3 or 7 second frame is amazing.
yeah, but this would probably be a longer frame than 7 seconds.
Okay.
I'm not sure what the camera settings were on this.
Just
We'd probably have a bigger one than
This
this.
guy's gonna keep it sturdy.
He's turning it off. I'm conscious of time now, so I'm just going to, let's see if anything. Structures, only a couple of slides and then we can, just for structures now, long distance, that's all. So the lenses, various lenses in the camera will allow you to zoom in to certain situations. We do this quite a little bit as well when you're looking at large structures. You can get measurements from off the top of something like that, if you wanted to, non-contact from the distance, and you can see with amplification certain things. It's how flexible the tools are, measurement points, non-contact from each one, each part, that type of thing.